All right, welcome, ladies and gentlemen, to our second lesson from Unit 7. We're looking at some more ways to anti-differentiate a function or a derivative or whatever word you want to use right there. We're going to learn the anti-differentiation by substitution method. This is how to find an integral using a very somewhat easy system here called substitution. So what I want to look at first is something to do with the differential. And what the differential is this piece here at the end, the dx, the du, or the dx. That's the differential. And this little statement here could show up somewhere, maybe in an AP exam or something like that. And evaluating these things from these given pieces of information using some sort of substitution. So the first one here, if I wanted to find the integral of f of x dx, well, that's saying I want to take the integral of f of x with respect to x, which means x is the variable in use. So that would look like this. I would take the function f of x, and I would integrate x to the third plus 1. And obviously, I think we all know that that antiderivative is x to the fourth over 4 plus x plus c. But as the question states at the bottom, what about something like this? If I want to do, I know you see the answer here. If I want to do f of u du, that means the statement in my integral has to have a variable u, and that's what I'm anti-differentiating with respect to, or integrating with respect to. So f of u is just going to be x to the third plus 1, because f of u here would be x to the third plus 1. We would take the antiderivative of that, which is u to the fourth over 4 plus u plus c. And then what we would do is we know that u is equal to x squared, and then we'd plug in x squared for u, so we get a final answer of x to the 8th over 4 plus x squared plus c. And the last question there, if I want to do f of u dx, well, that's a little bit more challenging because I want to do f of u dx, which means I start off with u cubed plus 1, but then I actually have to plug in x so I can anti-differentiate with respect to x. So here I would have u cubed. I would plug in x squared for u, so I'd get x squared cubed, which is x to the 6th. And integrating that gets x to the 7th over 7 plus x plus c. So notice the three different statements that look a lot alike all have three different answers, all based off of what the differential was and what the question was being asked. All right, let's look at the substitution method. You may have seen problems like this in previous work where it was something along the lines of 4 sine x cubed cosine of x dx. And you kind of have to see this as the chain rule derivative of sine x to the 4th power plus c. You have to see that the 4 comes down, becomes 3. The derivative of sine becomes cosine. Now, that is very handy to be able to see that, but there is something that we can do. It's called U substitution, and it will help us solve these questions a little bit easier if you see that one of the functions is the derivative of the other. So here's an example, a little bit different than the one I just gave. Some of us are going to be able to see how to do this problem or get this answer without needing the substitution. But what we can do here is we can say that let's find some function in here that one of the other functions is the derivative of. Well, I know, let's just say I know cosine is the derivative of sine. So let's just say we did this. And the derivative of u is cosine x. Well, here comes the problem. If I try to reset up this integral, I would have u e to the power of du. Well, that doesn't really work because there's no way that this would work. Okay, so that's just not right. Let's try something else. I know that the derivative of cosine is sine. That's actually the negative side. So I know that if u was equal to cosine of x, I know du is negative sine of x. So what I want to do first here, sine x dx. What I want to do first here is I want to rewrite this as compensating for this negative. What I want to do is I want to say it's negative sine x e to the cosine x dx. Now this step is not 100% necessary, but I want to show what I'm doing here. I'm negating the negative, so technically it's still the same question as before. I haven't changed it because the two negatives make a positive. But now I'm going to use the substitution. I have e to the cosine x. Well, cosine x is u. Oops, sorry. I don't know where the u came from there. E to the u. And then I know that negative sine x dx. So negative sine x dx, I know that is du. And now I know that the integral of e to the u is e to the u plus c. And then what I do is I know in order to put it back into an x equation, I need to plug back in my u function back into e to the u. So this becomes e to the cosine x plus c. And just like before, we can check our answer by finding the derivative of this. So we would get negative e to the cosine x times the derivative of cosine, which is negative sine, and I would get the original statement. So what this really is it becomes a process that you can solve some of the harder looking integrals. So here's some more examples. Here's one at least. I look at this question and I go, well, it looks like x squared is the derivative of x cubed. So let's see if we can do that. Let's say u is the whole thing under the radical. Therefore, du is 6x squared dx. The derivative of u, by the way, that's what we're doing. Well, I don't have a 6x squared, so I want to compensate. I want to say this is 1/6 of 6x squared. Notice I'm not changing the question. Times the radical of 5 plus 2x cubed dx. So again, my question is still the same. I just compensated for the 6 that I need here. So I get 1/6 of the integral root of 5 plus 2x cubed. Well, I'm going to change that to the square root of u. And then 6x squared dx is du. All right, so then I take the antiderivative here. The antiderivative of the square root of u is u to the 3/2 times 2/3 plus c. Then I finish my question here. I simplify. I get 1/9 times 5 plus 2x cubed to the 3/2 power. Plus c. Don't forget the plus c. I almost forgot plus c. All right, let's see. What do I have next here? Let's erase my screen. What about cotangent of 7x? Well, we don't really have an identity for cotangent, or an integral for cotangent. So what we're going to do here is we are going to change this to using a trig identity. We know this is the sine of 7x over the cosine of 7x dx. Then I'm going to use the same substitution as I used before. I'm going to say u is the cosine of 7x, and therefore du is negative 7 sine of 7x dx. Then, because I don't have the negative 7, what I need to do is I need to compensate with the negative 1/7 times negative 7 sine 7x over cosine of 7x dx. I was not paying attention to myself. Bad Mr. Nelson. I did tangent. Okay, let's try that again. Cotangent is cosine x 7x over sine 7x dx. In this case, I'm going to say u is the thing in the bottom because I can't put the dx into the bottom. So that's why I used cosine a minute ago, because I wasn't paying attention to myself. So u is going to be sine 7x. du is equal to 7 cosine of 7x. So now I can do a little compensation here. It's 1/7. 7 cosine 7x over sine 7x. And then I can do my substitution. 7 cosine 7x dx is going to be du over my u. And now I have a very simple statement. It's 1/7. The antiderivative of 1 over u is just the natural log of the absolute value of u plus c. And I get 1/7 of the natural log of absolute value of sine 7x plus c. Sorry for the mishap at the beginning of this. Not sure what I was thinking there. All right. So some of your problems are going to look a little bit tricky here. But there are things that you can do to them. In the first problem, the cosine squared of 2x in the denominator can be rewritten as secant squared of 2x dx. Then we can say, because we don't really know anything about like the 2x, what we can say is u is actually equal to 2x, where du is equal to 2 dx. So we can compensate for the 2 secant squared of 2x dx. I can substitute. I know I'm going through this kind of quickly, but obviously you have the advantage of pausing and that sort of stuff. Oop, that 2 doesn't go there anymore. Secant squared u du, and the antiderivative of secant squared is tangent. and u is equal to 2x. So we get 1/2 tangent of 2x plus c. All right, in the cotangent squared of 3x, what we can do here is we can actually use one of our other trig identities. We know the cosine squared is actually equal to cosecant squared 3x minus 1 using our Pythagorean identities. We can let our u equal to 3x, so our du is equal to 3. We can do our compensation. We can do our integration. We can substitute, and we can get a final answer. So notice this is kind of the process of what we're doing. If it's a trig function that doesn't show up as a derivative or likewise as an antiderivative, whatever on your blue sheet, what you can do is try to change it using a trig identity into something we do know. We know the antiderivative of secant squared, but we don't know how to antidifferentiate 1 over cosine squared unless we changed it. Same thing with cotangent squared. We can change it to cosecant squared, which then we can find the antiderivative, which is negative cotangent. For something like cosine cubed, what you can do is you can change it to cosine squared times cosine x. But still, we don't have one that's the derivative of the other, so we say, well, cosine squared is actually 1 minus sine squared times cosine squared. And now we can say that u is equal to sine squared and du is equal to 2 scratch that. Easier substitution. Obviously, that wasn't going to work because 2 sine blah, 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 that wasn't going to come out to this. So, you see, I still make errors sometimes too. If u is equal to the sine of x, then du is equal to cosine x. And then we have the integral 1 minus u squared du. And that one's easily found. All right, you can do the same thing with definite integrals. There are kind of 2 ways to do it. One, you just straight up do your substitution there at the very end by plugging your function back in for u, and then evaluate from 0 to pi. The way the textbook does this is, let's say u is equal to tangent, du is equal to secant squared x dx. And what you want to do is you want to do u of 0 and, u of pi. And what it does is it changes our limits of integration. Tangent of 0 is 0. And tangent of pi oh, no wonder this wasn't coming out right. That's supposed to be pi thirds. Change that to pi thirds. Okay, is root 3. And we go from 0 to root 3 of u du. And the reason this is nice is because now we don't have to deal with the trig functions anymore. We know that the antiderivative of this is u squared over 2, just evaluated from 0 to root 3. We've already done the trig part of it. Now we can just use the substitution to answer our question. Root 3 squared is 3 over 2. If I plug in a 0, I get 0, so my answer is 3/2. And that will finish us off. I hope you learned a little bit, even with my couple errors that I had up here. I will see you guys tomorrow.